Okay, now let's look at several examples of chapter 7, the energy principle. Okay, the first problem I want to talk about is example 7.3 in the textbook. Okay, so this is the drawing, the problem. Okay, there's a pipe. Okay, there's a pump to pump the flow in the pipe from a low location to a high location. It's a typical pump application, right? The flow rate in the pipe is 0.5 cubic meter per second. Okay, the diameter of the pipe doesn't change. It's 0.5 meter. That's the diameter for the pipe. The elevations, the inlet elevation is 30 meter. The outlet elevation is 40 meter. So there's a 10 meter of rise. Okay, pressure at the inlet is 70 kPa. At the outlet is 150 kPa. So the pump not only delivers the flow from lower location to high location, but also increase the pressure of the flow. Okay, so that's the problem statement. Okay, one more thing. There's a loss. The total loss for the pipe is 3 meter. Okay, that's a high loss, right? So this is obviously a conservation of energy problem in the pipe, right? The question is ask you to calculate the power required by the pump to make this system work. So basically, how much power is the pump needed to add into the pipe to deliver the water from low location to high location, as well as to increase the pressure from 70 kPa to 150 kPa. So what is the power required by the pump? Okay, it is water. Notice the alpha is 1, gamma, the specific gravity is 9810 for the water. Okay, so obviously this is a conservation energy principle problem in the pipe. So you want to write down the equation. Okay, this is the equation, right? P1 over gamma plus Z1 plus V1 squared over 2G plus a pump head. Yes, we have a pump equals P2 over gamma plus Z2 plus V2 squared over 2G. And we don't have a turbine, so no turbine head, but we do have a loss plus HL. Okay, so the velocities are the same. Okay, they are not equal to 0, but they are the same. Conservation of mass. Okay, the velocity, the flow rate has to be the same in and out, so the velocity has to be the same. The diameter is the same, right? So you can cancel the velocity V1 and V2, right? Velocity head are canceled. So we know everything, right? Except the HP pump head. So that's the purpose. After we calculate the pump head, we can calculate the power. So do we have everything else? I think we do, right? We know the pressure P1, gamma, and the Z1 30 meter, okay? Pressure P2, 150 kPa, and the Z2 40, and the loss is 3 meters. So simple calculation. So pump head is 41.5 meter, okay? So you need a 41.5 meter of pump head to make the system work. Okay, so what is the power? Remember the power equation, right? Gamma, volumetric flow rate, and the times pump head. If you have a pump head, basically simply just times the property, right? Gamma, then times the flow rate. So we can calculate it's 204 kilowatt, 204,000 watt. That's the power needed from the pump to make this system work. Okay, so this is 7.3. So now let's look at the 7.4. 7.4 is a turbine problem. Okay, so the problem is like that. You have a reservoir, high reservoir. Okay, you flow the river water down from the reservoir to a lower reservoir. Okay, the high reservoir is 61 meter. Okay, the lower reservoir is water level is 0. Okay, so you have a turbine that is out of the flow to convert all the kinetic energy, potential energy into power, into electricity, right? Turbine, you take energy out of the system. So the question is, what is the turbine actually, the electricity power you can receive from this system? Very practical problem, right? The known values. Flow rate, again, it's given 14.1 cubic meter per second. The total loss for the system is 1.5 meter. Okay, elevation 61 to 0. The turbine efficiency is 87%. Okay, so not all the energy you get from the system will turn into electricity, right? Only 87% of them. Okay, so again, this is the conservation energy problem. Write down the equation. Okay, this time you don't have a pump in the system, so no pump head. Instead, you have a turbine head in the right hand side. Okay, so reservoirs, open surface, so P1, P2 are all both 0. And the V1 and the V2 on the surface, obviously we pick the point on the surface, both surfaces, right? So velocity are also 0 on the surfaces. So it becomes turbine head is just equal to Z1 minus Z2 minus the head loss. So Z1 is 61, Z2 is 0, and the loss is 1.5 meters. So the turbine head is 59.5 meters. So the power calculation, okay, gamma Q turbine head times efficiency. Remember, times efficiency here, right? That's the actual power you will receive from the system. So actual power is about 7.16 million watt. There's a lot of power you can get from the system like that. 61 meter drop of water can give you more than 7 million watt. Okay, so these are the two examples. Let me give you one more example. Okay, the next example is example 7.5. 7.5 is a little bit more comprehensive, okay? So it is a nozzle, water flow in the nozzle. The nozzle, the diameter inlet is 0.5 meter and the diameter at the outlet is 0.2, right? It's a contraction. Okay, the flow rate is still given, 0.707 cubic meter per second. Okay, the pressure inlet and outlet, pressure inlet is 250,000 Pascal, but at the outlet, P2 is unknown. Okay, we don't know. We probably need to figure it out. And the loss, this time the loss is not a constant. Okay, it's an expression. It's a function of V2 at outlet velocity. Okay, so it's 0.1. The loss equal to 0.1 times V2 squared over 2G. Okay, it's an expression. So we need to find out V2 and we can calculate the loss. Okay, so the question is to calculate the force required to hold this nozzle in place. Okay, the force required to hold it. So it's similar. It sounds familiar, right? This is a chapter 6 problem, right? It's a conservation. Obviously, you're calculating a force required to hold the nozzle. It must be conservation of momentum. So I think for this problem, your starting point is conservation of momentum. Okay, so let's review how we do conservation of momentum, right? So we need a free body diagram and the momentum diagram for this problem. Okay, free body diagram, you have pressure forces from inlet and outlet, P1, A1, P2, A2, and the force required to hold this nozzle in place. I put a positive x direction force F. Okay, and the momentums, very simple problem. Momentum have two momentums, momentum in and the momentum out. I use mass flow rate times V1 as momentum in and the mass flow rate times V2 as momentum out. Because mass flow rate is the same inlet and outlet, right? So I can use the same ladder. So the equation, right? After you draw this diagram, put the equal sign, and left side is summation of force, right side of the equal sign is summation of momentum, right? So P1A1 minus P2A2 plus F, that's the force balance, right? Equals momentum out minus momentum in. Both momentum are positive, so momentum out minus momentum in. So we are calculating the force F, right? We need to know everything else. Do we know everything else? At least we know P1A1, right? Diameter we know. So we know P1A1. We don't know P2. Okay, and we know A2. How about the mass flow rate and the velocities. Okay, we're given a volumetric flow rate. Okay, so mass flow rate is just equal to the volumetric flow rate times the density of water, right? Easy. So mass flow rate times V2 minus V1. Okay, so in order to calculate F, probably we need to find out V2, V1 as well as P2. Okay, V2 and V1 are easy. We are given the flow rate, right? Volumetric flow rate. So V is velocity is volumetric flow rate divided by the cross-sectional area. So V1 is Q divided by A1, right? Quarter pi D1 square. V2 is Q divided by A2, quarter pi D2 square. So 10 meter per second is the inlet velocity, and the 22.5 meter per second is the outlet velocity. Okay, that's easy. So V2, V1, we find it out. Okay, so the next goal is to find out P2. So how do we find out P2? Which equation we're going to use? This is chapter 7, right? Obviously now we're going to use the equation for chapter 7, the energy equation in the pipe, right? So we write down the equation. P1 over gamma plus Z1 over plus V1 square over 2G equals P2 over gamma plus Z2 plus V2 square over 2G. No turbine and no pump in this case, so only loss, plus 0.1 V2 square over 2G. We have the expression for the loss. Now, we know everything, right, in this equation except P2. V1, V2 we already calculated. P1 is given. Z1 and Z2, they're the same, on the same elevation, so it can be cancelled. So based on this equation, simply you can calculate the P2, 21,600 Pascal. Okay, then you substitute P2 into this equation. We know everything, right? V2, V1, and we know P2. So the force required to hold it is negative 8,160 Newton. Simple. Okay, based on the calculation. So it's a negative force. So basically the force direction is to the left, right? You have to hold this nozzle in place. So the flow is to the right. So the force required to hold it is to the left. Okay, so that's a more comprehensive problem. Okay, and we use the knowledge chapter 7, chapter 6, as well as chapter 5, right? Conservation mass, the flow rate is the same. Okay.